Welcome everyone. Thank you for joining us for episode 26 in the Gleeble webinar series. This is Dan Quigley with DSI, and I'm happy to be your host today. There's a lot of news lately about the rising number of coronavirus cases in many parts of the world, so I hope everyone out there is staying safe and taking the appropriate precautions. We're happy to do our part by hosting these webinars from multiple, very distant offices around the world. We do appreciate you spending time with us. We have a very interesting presentation today focused on forging tooling and workpiece forming. As always, our goal will be to keep this webinar to 1 hour or less. If you have questions during the presentation, please submit them using the chat feature here in the webinar. We have a few team members here that are available to answer some questions directly via the chat, and if time allows, we will have a Q&A following the presentation with the team from Hannover. Video of this presentation will also be available online soon, and certificates will also be emailed to you if you are listening to this live. You will be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and then clicking on the resources link in the top navigation bar. Then click on webinars. There you can view past webinars and sign up for future webinars. Next week's session will feature a presentation by Professor Cecilia Poletti from Graz University of Technology. Dr. Poletti will present her research on aluminum alloys in both processing and end-use applications. So we often focus on steel in these webinars. However, a lot of our users are studying other materials. So I'm excited to hear Dr. Poletti's discussion of how they are studying aluminum applications on a laboratory scale to better understand the relationship of microstructures and loads and how those findings can be used to design high-performance products. Today, I'm happy to welcome Mr. Maiwand Hootak and Mr. Christoph Kock from the Institute of Forming Technology and Machines at Leibniz University of Hannover. Their presentation is titled Material Characterization and Forging Simulations, focused on workpiece forming and workpiece forming behavior and tool fatigue. Gentlemen, I want to thank you for taking the time to prepare this presentation and sharing it with us. I will now hand this over to you. The floor is yours.
Thank you, Dan, for your kind introduction. Ladies and gentlemen, welcome to the presentation on the material characterization and forging simulations focused on workpiece forming behavior and tool fatigue. My name is Christoph Kock. Together with my colleague Mr. Hootak, I will give the presentation today. We are both research engineers at the Institute of Forming Technology and Machines in Hannover, Germany. In Germany, our institute is just known as IFUM. IFUM is part of the Leibniz University of Hannover. Here you can see some facts and figures about the university. We have, for example, 113 million euro third-party funding, almost 5,000 employees, thereof over 300 professors. There are 86 study programs and currently almost 30,000 students. The Faculty of Mechanical Engineering, as part of the University of Hannover, has 19 institutes. These are classified into the focal areas of design and development, engineering and process technology, production engineering, and logistics. In turn, part of the Faculty of Mechanical Engineering is the so-called Hannover Center for Production Technology, short PZH, to which IFUM belongs. Within the PZH, around 270 engineers and natural scientists research and teach in 8 institutes of the Leibniz University. In addition, engineers from TEVIS and numerous smaller production technology companies work here. Many of them are spin-offs from the institutes. To give you a visual impression of where we work and research, I show you a current photo of the campus of mechanical engineering. Some of the buildings at this location are brand new and were opened in 2019. However, the IFUM has been based here since 2004. Now that you know who we are and where we work, let's move to the agenda for the Gleeble webinar today. Our presentation is structured as follows. First, I will give an overview of the research area of the IFUM. There are a few. I will discuss the possibilities and expertise we have at IFUM, the fields of sheet metal forming, bulk metal forming, regarding forming machines, and material characterization and simulation. Since my colleague and me are working in the field of material characterization and simulation, the following will mainly deal with these kind of topics. I will talk about the possibilities and requirements for flow curve recording for hot forming simulation. Mr. Hootak will then go on to discuss life cycle analysis under superimposed mechanical and thermal loads. The IFUM deals with both basic research and current application-oriented questions from almost all areas of metal forming technology. The Institute's expertise in research and development covers innovative processes and methods of cold and hot forming, future-oriented machine and tool concepts, as well as the handling of novel materials and composite materials in experimental and virtual aspects. As said before, the Institute's core competences include the focal areas of sheet and bulk metal forming, machines for forming technology, as well as material characterization and simulation. In the following, I would like to briefly present the technical possibilities of the IFUM and just pick out some of the current research aspects of the IFUM for an in-depth look. The sheet metal forming division is engaged in basic research as well as in close cooperation with industry in application-oriented research. The subject areas include process development, process management, quality assurance, tribology, light-weight constructions, or mechanical joining. One example of the field of process development is press hardening for the tailored production of functional components. Form hardening is a process of hot sheet metal forming, which is mainly used in the automotive industry. In this process, a sheet is heated to a temperature of over 900 degrees Celsius and cooled in the tool during the pressing. This produces a martensitic structure with high strength. Automotive engineering, for example, often requires components with locally varying properties. For example, the B-pillar of a passenger car must have high strength in the upper area to protect the passengers. In the lower area, there should be higher ductility of the material so that the energy can be absorbed in the event of a crash. One question for the IFUM was therefore, how can we produce such parts economically? The solution is a special spray field cooling, in which water and air spray is applied to the component areas to be hardened, while other areas are cooled slower. In our video, you can see an example process where a demonstrator component is treated in this way. After the sheet metal has been heated up in an oven, it is inserted into the tool, formed, and then transferred to the spray cooling. Subsequently, the partially adapted cooling takes place. As a result, we see here in blue the hardness curve of the demonstrator component after tailored processing. As a reference, we also see the hardness curve of a conventionally press-hardened profile in red and a profile cooled in air in green. By partial cooling, the hardness profile could be adjusted as desired. The area of bulk metal forming is concerned with basic research on the forming technology of innovative material concepts, the development of and optimization of forming processes, and tribological property investigations. Other areas of research include powder metallurgy, lightweight metal forming, or process monitoring. An exemplary research area is the use of metal matrix composite materials, short MMC, as forming tools. MMCs consist of a continuous metal matrix with a discontinuous ceramic or organic reinforcement in its interior. For example, fused tungsten carbides, here WSC. Such tools can also be functionally adapted, produced with different mass proportions of material additions, and combined with classical tool steels, for example, by diffusion joining. At IFUM, we develop such tool concepts and also test them in the process. In the video, we see how a punch made of the MMC material is used in the forging process to produce a reverse extrusion cap. As you can see from the flame, this video is in slow motion. Furthermore, the tools are also tested in continuous operation, and such tests are repeated several hundred times. The wear investigations show that the conventional tool steel is more affected by the process than the MMC materials. At the bottom of the slide, it can be clearly seen that the addition of the hard WSC phases prevents the material from being removed after 100 cycles in this experiment. In the area of forming machines, both basic and applied research is carried out with the aim of introducing and optimizing machine technology used in forming production. Furthermore, research is carried out into processes in which the influence of the machines used on the quality of the manufactured components is particularly high. The focus here is on electromechanical drive systems, control systems, measuring technologies, machine simulation and evaluation. Furthermore, process analysis regarding processes like shear cutting, embossing, or leveling is carried out. An example from the field of forming machines is the high-speed blanking press. It works with electromagnets and integrated tilt compensation, which enables stroke rates of up to 1,600 per minute. To illustrate the speed, I have a video on the next slide. This time the video is played in real time, and not faster. Let us move now from the forming machines to process simulation, the area in which my colleague Mr. Hootak and I are working. Our aim is to numerically represent the entire process chain of forming operations for a profound process analysis and optimization. This means, for example, that to simulate a forging process, as shown on the slide on the right, we simulate the heating process, the forming process itself, and also any heat treatment steps. For this purpose, we have numerous possibilities for material characterization on different testing machines at IFUM. Besides material characterization and process simulations, the expertise of the IFUM lies in the fields of material and friction modeling, microstructure transformation, simulations, as well as biomedical sciences in combination with forming technology. A development from the field of material characterization and simulation is, for example, the damage characterization using the so-called variable grips, which are shown on the left side of the slide. With these variable grips, depending on the angle of tension, numerous different stress states can be generated in the shear specimen, the so-called butterfly specimen. This way, stress-based damage models can be parameterized in detail, as shown in the picture in the middle of the slide. This method can be used to characterize a much wider range of stress states than is possible with a classic forming limit curve. To improve the numerical analysis of formability, for example, in deep drawing. Two further topic deals with friction and tool wear in hot bulk forming. The friction in the massive forming process is, for example, mainly driven by the contact pressure and the relative speed between workpiece and tool surfaces. In recent years, the so-called IFUM friction model has been developed, which takes these two physical parameters into account. This friction model has even been integrated into the commercial software Simuvec Forming and is therefore available to numerous users. On the right, we see the evolution of a pinion shaft in the course of the process chain. If we put some of our expertise together, it is now possible to virtually view the complete process chain of this kind of products. Now, as you got to know our institute's research work, I would like to introduce our Gleeble 3800 GTC that we have been applying since 2018. As an all-rounder for material characterization, the Gleeble, with its numerous experimental possibilities, fits very well in the philosophy of our institute. We want to consider the processes in their entirety, while not leaving out any aspects of manufacturing. This means that we look at the process in terms of both workpiece and tool behavior, and at the process itself from preparation to the actual forming process and any finishing steps. Our Gleeble is equipped with a general purpose unit in which we can perform many different types of tests with the high maximum possible stroke, speed, and temperature. This includes application from the determination of temperature-dependent flow curves over generation of CCT to thermo-mechanical fatigue experiments. In our first application example, I would like to discuss the requirements of material characterization from our point of view as numerical scientists. For this purpose, we consider the necessary material data for a forging simulation. Our example shows the production of a piston by forging with burr. The desired geometry of the piston is shown in the sectional view below. The simulation is created with simultaneous forming and solved with the solver MSC Mark. The tools are modeled as thermally conductive rigid bodies. The workpiece is meshed with hexahedral finite elements, and the so-called GMT model is used to calculate yield stress. Thereby, the yield stress is calculated as a function of strain rate, temperature, and by using an empirical equation. On the right side, we see the result of the forming simulation with regard to the resulting equivalent plastic strain. In order to carry out such a simulation close to reality, material characterization tests had to be carried out in advance. For this purpose, upsetting tests were carried out on our Gleeble to determine flow curves. Cylindrical specimens with a diameter of 10 mm and a height of 50 mm were used, which were equipped with welded-on thermocouples. The tests were carried out isothermally at different temperatures in the relevant range of hot forming from 900 to 1200 degrees Celsius. In addition, different forming speeds in the range of 1 up to 50 per second were considered. The determined flow curves were used to calibrate the previously mentioned empirical approach of the GMT model in order to enable a continuous stress calculation in the simulation. On this slide, we now see the temperature development of the workpiece material during the forming process. We notice that during the forming process, which takes place in less than 1 second, a significant temperature gradient is established in the material. At the surface of the material, there is a temperature of about 900 degrees Celsius at the end of the forming process, while inside the component, there are still high temperatures up to 1200 degrees Celsius. As is typical for forging processes, the tools were modeled in the simulation at a temperature of about 250 degrees Celsius. This explains a significant cooling of the material by the tool workpiece contact. Furthermore, the simulation also takes into account the heat release due to plastic deformation, which explains the permanently high temperatures inside the material. As can be seen by the flow curve in the diagrams on the left, this observed temperature gradient means that locally different flow stresses and consequently different forming conditions prevail. It demonstrates how important the temperature-dependent material characterization is. In the same way, we can calculate the strain rates that occur in the material. In this model, a screw press with a maximum speed of 670 mm per second is considered. The video shows that local equivalent plastic strain rates of more than 100 per second occur in the component. Again, the strain rate gradient results in locally different flow conditions as shown by the flow curves determined in Gleeble. If we think back to the slide on which the equivalent plastic strain distribution on the material was shown, we can be sure that without this temperature and strain rate dependent material characterization, the material flow would have been simulated incorrectly. With this application example from the point of view of a simulation engineer on the importance of material characterization, I would like to end my part of the presentation. I hope that you enjoyed my slides and videos, and I hand them over to my colleague, Mr. Hootak, who continues the presentation about tool fatigue.
Yes, thank you very much, Christoph. Hello, everybody. My name is Hootak, and I would like to continue with the second application example, namely the low cycle fatigue investigations for tool life predictions in tixoforming. So first of all, what is tixoforming? Tixoforming is a forming technology that takes advantage of the semi-solid material state. So the microstructure of the material exhibits a liquid phase with solid particles embedded in the melt. Under stress, the globulitic solid particles rotate and translate in the melt, whereas in the dendritic microstructure, the melt is pressed out. So as you can see in the figure, when the material or the workpiece is in the semi-solid state, you could cut this workpiece by bare hand into two pieces. Therefore, thixoforming possesses technical and economic potentials, since high-loaded and complex-shaped parts may be manufactured within a small number of process steps. Besides, low power and energy are required, and near-net shape-forming production, as well as extension of the component classes, are possible. The comparison of the conventional forging with thixoforging of the connecting rod highlights the smaller number of process steps. You can see that in these pictures many examples of three examples of thixoformed serial parts made of aluminium. So serial parts made of aluminium are well established in industry. However, thixoforming of steel alloys is still in pre-industrial stage. Because producing steel parts is still challenging due to the high process temperatures, that is why an FE-based process design is necessary for reasons of cost efficiency. So one big problem is that the true life is reduced because of the high process temperatures. That's why an accurate calculation of true life in the thixoforging processes of steel parts is important. For this reason, we need a certain material model. In this case, in our work, we model the material by deriving the corresponding functions. During thixoforming process, the material adopts both a solid and a thixotropic state, as different areas of the workpiece reach different temperatures. Thus, areas below the solidus temperature require a structure-mechanical description. We used, for example, the Hansel-Spittel equation, whereas the areas exceeding the solidus temperature are described by a fluid mechanical model, such as Oswald-de-Velde approach, which we use in this work. And this relationship can be expressed, for example, by a section-wise defined function, and then it can be written as a subroutine in the FE software. We applied the commercial FEA software package Simulfact forming, and one problem is that these FEA software packages have databases where the flow curves for hot forming, for example, is included in the material databases, but flow stresses values for temperatures above 1250, for example. So when the temperature ranges of hot forming are temperatures are above this one, then the flow stress is assumed as constant. And the comparison of offsetting test illustrates the significant difference between the applied models, because you can see that the effective stress values in the workpiece material are approximately 3 times higher than the ones computed with the user-defined model. When the material temperature reaches the melting range, the flow stress decreases clearly. This aspect is not considered by the default material model, as the flow stress is assumed as constant for temperatures exceeding common ranges of hot forming, in this case above 1250 degrees C. And this could be verified by offsetting tests of semi-solid specimens applying the Gleeble system. The forces were much lower than the computed ones using the default material model from the database. So, in addition to an accurate material model, we also need to know more about tool failure to calculate tool life. It is state-of-the-art mechanisms such as abrasive wear, mechanical crack initiation, thermal crack initiation, or plastic deformation influence tool life in forging due to diverse thermo-mechanical loads. These mechanisms apply to thixoforging as well. However, the main loads are tribological, thermal, or corrosive. So next, we need an approach to calculate damage in the tools, such as the Tools life prediction approach, which takes three different mechanisms into account. So the total damage is calculated by the sum of the corresponding proportions of which the reciprocals are the cycle numbers until crack initiation. Fatigue damage is represented by the classical fatigue mechanism, which normally occur at ambient temperature. These include crack nucleation and propagation due to the strain amplitude. Oxidation damage mechanism includes crack nucleation in surface oxides and oxide-induced crack growth. Creep damage is observed in the form of internal intragranular cracking at the grain boundaries. Now we need a process where we could implement our material model as well as the true life prediction model. For this purpose, following process of a thixoform forging of a cup was simulated. Due to the rotational symmetry, a 2D model was sufficient, in which every step of the real process, including the transport of raw parts from the heating equipment to the forming equipment, was simulated. But the life model needed to be parameterized, therefore. It needed to be parameterized. So the so-called low cycle fatigue, LCF, and thermo-mechanical fatigue experiments were performed using the Gleeble system. The process window was determined beforehand by means of FE simulations, taking into account different degrees of deformation, strain rates, and the temperature loads experienced by the two. The tests were carried out as mentioned in the physical forming simulator system Gleeble at the IFUM to parameterize the model. During the LCF tests, the specimens were cyclically loaded with a constant strain amplitude isothermally in atmospheric air. In addition, so-called in-phase as well as out-of-phase thermomechanical fatigue tests were performed, where the amplitude of temperature oscillating between 300 and 750 degrees C and strain are in phase or have a shift of 180 degree, respectively. Notification of crack initiation is possible by the change of the stress amplitude and its sudden drop. In this work, the crack criterion was fulfilled when the value decreased by a minimum of 50%. Following figures show the fracture regions of the specimens after the corresponding different types of thermomechanical cycle fatigue tests. Micrographs were taken by means of grinding longitudinal sections. Therefore, pieces from the failure areas were taken from the specimens by wire erosion, which were subsequently etched to make the microstructure visible. When the LCF test is performed at room temperature, the sample is only subjected to mechanical stress. Here, the main mechanism for sample failure is pure fatigue. Due to dislocation movements caused by the load change of tensile and compressive stresses, cracking occurs in the forming zone and the material fails when the critical crack length is reached. So in this case, cracking occurred after 78 cycles. For the specimen treated by the OP TMF loads, oxidation occurs in the hot work steel. The pictures illustrate the representative surface oxide and oxide intrusions. During the thermomechanical loading, the first oxide layer cracks so that the exposed metal surfaces oxidize again. It is typical of OP cases that an oxidation damage mechanism dominates, where the maximum temperature acts on the material concurrently to compression stresses, since void growth and intergranular cracking mechanisms are suppressed in compression. Here, cracking occurred after 21 cycles. In contrast, no oxide intrusions formed in the in-phase TMF case. Here, most of the damage occurs in the form of internal intergranular cracking at the grain boundaries. Micropores are visible at the grain boundaries, which lead to the formation of macropores in adjacent areas and eventually crack initiation. The main damage mechanism is creep because tensile stresses coincide with high temperatures promoting void growth. The performance of the above-mentioned LCF and TMF tests confirm the findings of the studies in literature, and the cracking occurred already after 9 cycles. The main purpose of the experiments in this work has been to determine the parameters of the tubular model for the tool material under investigation. Therefore, after the test, the model equations were determined. Corresponding curves for the different cases of tests were calculated and displayed in the depicted figure. The comparison shows that the calculated curves can predict the cycle number fairly accurately. Subsequently, the total tubular model was implemented in simulfact forming by means of the user subroutine. The LCF tests have shown that the room temperature strain life curve can be considered an upper bound on life. In the TMF tests, the achieved cycles of all test specimens were found to be less than those during room temperature tests. Any decrease in life can be attributed to oxidation effects, creep effects, or both. The total strain amplitude cycles until crack curves are illustrated in the figure for the three cases of isothermal LCF tests, thermo-mechanical, OP, as well as IP tests. Afterwards, a cup backward extrusion process was investigated. The figure shows the numerical and experimental results. By comparing the punch in its initial state with a worn and deformed one after 20 cycles, it is evident that relatively high degrees of deformation of the tool material occur due to the high heat input, accumulating from cycle to cycle. This leads to decreased yield stresses and thus to plastic deformation, which simulation could predict in advance. Due to high thermomechanical loads, the implemented fatigue life model predicted that the total number of cycles in total was about 15 until failure in the mandrel radius area. The experimental results showed the condition after 20 cycles and confirmed the numerical results by the enhanced damages at the same location. This state of damage may be considered as tool failure. Now we'll summarize the main points of my talk. In this work, numerical investigations of tool life and fixer forging of steel parts have been presented. For this purpose, at first, the tubular's life model was introduced in consideration of the three damage mechanisms. Afterwards, results of the LCF and TMF experiments performed on the Gleeble system were shown. Micrographs of the specimens after cracking confirmed the aforementioned damage mechanisms occurring as main causes for material failure in such tests. Besides, these results made the determination of the tubular's model parameters possible. The model equations have been implemented in simulfact forming by a user subroutine. A comparison of numerical and experimental fixer forging results demonstrate a high correlation. Yes. Now I'm finished, and first of all, thanks for their attention, and if you have any questions, feel free to ask. Thank you very much.
Great. No, thank you. This is a very interesting presentation. Maiwand and Christoph, appreciate you guys going through your research and giving an overview of the organization as well. We do have a few questions here, so I may ask you to move back into the presentation a little bit. One of the questions referred to slide 29, and probably a couple slides before that as well. The question said, did you compare the flow curves obtained from the Gleeble with ones from commercial software JMAT Pro?
Oh, no, I didn't. But it's an interesting question. We also use JMAT Pro for investigations, but for the hot flow curves, we in almost every case we use the experiments by Gleeble and not use some calculated flow curves.
Okay, great. A couple of questions here relating to the high temperature compression work you're doing. So the first question is, what are the difficulties faced to make such experiments of compression at high temperatures? And then a follow-up question, which I'll also ask you about the anvil types that you used, looking at what type of tooling you were using for anvils.
In which case, what for anvil types?
It was right. So the flow stress or uniaxial compression testing that you were doing, what types of anvils were you using?
Oh, normal tungsten carbide anvils.
Okay, because these are, I think it looked like you were doing some testing above 1200. So did you have any challenges with those? Were they breaking? You were able to get, I guess they worked okay?
Yeah, we saw after experiments at these high temperatures, we saw them break faster than at lower temperatures. Maybe just after 2 or 3 experiments, we had some cracking or abrasion on the surface of the specimen of the tools.
Okay, so I know that our team has been experimenting with different anvil materials as well to look at higher temperatures, and it's something that always is a challenge for us is doing these strong materials at high temperatures. So there are some new options out there. I think they're most part they're still in testing, but they've been working well. So I'll offer that up to anybody that's interested in going higher temperatures. Reach out to David Jacon, who is I think everybody knows Jake, but email us parts@gleeble.com, and I think they can talk to you a little bit about those types of anvils. We have a question here. I'm not sure if you'll have an answer for it, but I'll ask it anyway. It says, can you use the thixoforming process for a mixture of polymer metal powder feedstock? It would require lower operating temperatures. However, a post-processing is required to remove the polymer. Is that something that you've looked at all or can comment on?
Can you repeat the question? The material was powder? Have I understood you?
It says, can we use the thixoforming process for a mixture of polymer and metal powder feedstock?
Actually, we in our research work, we also have experience with powder metallurgy, where we can mix different kind of alloys. So this is the main advantage of powder metallurgy, that we can adapt the properties of the workpiece by mixing different alloys, and it was, and it also was used in thixum forging, yes. But we haven't tested it on the Gleeble system with powder specimens.
Oh, okay. The next question, I believe, relates to slides 37 or 38. And the question is, have you studied tribological properties of tool wear? I think you're there
this one?
now. Yep, it says, have you studied tribological properties of tool wear?
The next steps are that we want to also to study the tool, so the forging, thixoforged forging was performed, and then we have to study what kind of damage mechanisms do play an important role in this case. So we haven't studied it, but this is the outlook for next steps.
Okay, great. Slide 42, there's a question here, and you may have mentioned this, and I apologize. The question was, what is the tool material that was studied in the low cycle fatigue investigations for tool life predictions? What is that material?
It's a hot steel tool, hot tool steel. So it's 1.2367, so 1.2367.
According to international standards?
Yeah, according to the international standards.
Okay, great, thank you. And I think we only have one more question here. And this is in the first part of Christoph's presentation. I believe you mentioned changing the applied stress state by use of fixtures. And what stress states were studied using the Gleeble? So I can read that again. And again, I believe, Christoph, this is the first part of your presentation.
I think it's about fracture characterization.
I believe so. It says you mentioned changing the applied stress state by using fixtures. So what stress states were studied?
Oh, it was a wide range of stress states. We had them from triaxiality equal to 0.33 to triaxiality from minus 0.1, I think.
Okay.
And we can test some more triaxiality states in higher ranges.
Okay. And one last question. So in your presentation, you talked about the quenching setup that you had created, actually quenching the actual piece. Did you use any of the Gleeble quenching capabilities in your testing? I think you used that. Looks like it was a custom-built quench system you had set up. Used water and air spray. Did you utilize any of that in the Gleeble as well?
Yeah, we have realized it, but we never applied the water quenching. Mostly we applied in Gleeble the air quenching or quenching by gas. Maybe
Okay.
for recording phase-dependent flow curves for supercooled austenite or something like this.
Okay, great. And then one last thing. So last week we presented about digital imaging correlation, and that's something that we see a lot more people interested in. Have you used DIC at all on your testing? I think especially with looking at forming or a number of different applications. But is that something? Do you guys have a DIC system, or is that something that you have used either with the Gleeble or outside the Gleeble?
Yes, we have a DIC system, but we not used it on Gleeble yet. But we are planning to do this.
Great. I think that'll be interesting. So love to hear how that goes when you get to it, and I think our team can help you set that up if you'd like. So again, I think that's it for our questions. I do appreciate Christoph and Maiwand taking the time to develop the presentation and sharing it with us. I do want to be respectful of everyone's time. Actually, we're going to end a little bit early today, which is great. I'm sure people can find something to do with that free time. If you do have questions for the team at Hannover, or if you'd like to connect with them directly, please feel free to reach out to me. I can share contact information and help you make that connection. If anyone out there has technical questions about the operation of their Gleeble, please contact our service team. As I mentioned every week, the best way to do that is to go to our customer support portal. And again, that's you can get to that by going to gleeble.com and clicking on the resources link, and then go down to the customer support portal. If you're a Gleeble user, you can create an account. And then once you're in there, you can search the knowledge base or create a support ticket. And that really is the best way to get support. So I hope you do take advantage of that. If you have any questions about how Gleeble can support your research, please email really anyone on our team, but you can reach out to me for sure, and we can connect you with an application expert focusing on what you're focusing on, or it's in your region. We can help make that connection as well. Again, I want to thank you all for joining us, and we do appreciate your time, and I hope everyone out there stays safe and healthy. Have a great day.
Have a nice day.
Bye.
Bye.